Good evening. Good evening, everyone, and welcome to the inaugural College of Engineering Dean's Distinguished Lecture. My name is Scott Ashford. I'm the Carney Professor and Dean of our College of Engineering here at Oregon State University. Tonight, we reflect on the past, present, and future of innovation at Oregon State. Not only are we celebrating Oregon State University's 150th anniversary, but we are recognizing the legacy of someone who embodies the true meaning of an Oregon State engineer. And in the coming years, we will witness the global impact of the technology that started right here on our campus. It's a powerful story of one of Oregon State's most successful commercialization efforts, and it's a demonstration of what is truly possible when innovation, entrepreneurship, and philanthropy intersect. José Reyes, Professor Emeritus of Nuclear Engineering, held the Henry W. and Janice J. Schutte Endowed Chair in Nuclear Engineering and Radiation Health Physics since 2003. He is a member of the National Academy of Engineering and is the Chief Technology Officer and co-founder of NuScale Power. NuScale Power, a nuclear technology company, was launched from research that Professor Reyes led at Oregon State University's College of Engineering in the early 2000s. It's a small modular design, the first of its kind, and is poised to come onto the market in the mid-2020s. Professor Reyes is internationally recognized for his expertise in nuclear reactor safety and thermal hydraulics. He was a faculty member in the College of Engineering for more than 30 years. He served as head of our Nuclear Engineering and Radiation Health Physics Department, director of the Advanced Thermal Hydraulics Research Lab, and was co-director of the Battelle Energy Alliance Academic Center for Research Excellence for thermal fluids and reactor safety. He also managed the AP 600 and AP 1000 reactor integral system design certification test programs for Westinghouse, and the Nuclear Regulatory Commission has certified both designs using world-class test facilities right here at Oregon State. We are proud to have Jose be part of our community, and we are thrilled to hear from him tonight. So presenting a lecture called Innovating Our Energy Future, please join me in welcoming José N. Reyes.
Well, it's nothing like having 500 of your closest friends and family come visit tonight. So this is awesome. Thank you so much for being here. It is truly an honor to be part of this family. It is an honor to be part of an institution that really cherishes innovation and promotes it, encourages it, and really helps support it. So before I get too far into my presentation, I want to express my warmest thanks to my wife, Donna, who 42 years of supporting this effort. So, this is an honor that I'll remember for many, many years. There's been other honors, and so I listed a couple of memorable honors here. I shall do it. So some of you may have met Janice and Hank Schutte. Janice and Hank provided the endowment for the first chair, really, in nuclear engineering at Oregon State University. And when things got difficult sometimes with the company, I'd give Hank a call. Say, hey, this is what's going on. And he'd say, oh, you got to keep going forward. This is going to be great. You can do it. so I think I'm too old for this, Hank. No, you're fine. You'll be able to do it. So he was always an encouragement to me personally. But it just shows what philanthropy, what an endowed chair can do. It can free up your time so that you can do this kind of cutting-edge research. Another big recent event, this past Sunday, I was inducted into the National Academy of Engineering. And so that was a truly exciting honor for me. It was a great event. You have this great ceremony, a black tie dinner, and then the next day they put you to work. It's like, and you're working for free, it's public service. So it was interesting to meet my new colleagues there in the academy and see the really some groundbreaking studies that are being done by the academy. It's great to be part of that. Another really memorable event. Another memorable event. Oh yeah. Now I had to practice a couple of weeks to get that pitch just right. So I got to throw out the first pitch at an OSU game, and that was really one of the big highlights. I've always wanted to do that. And man, was I sore. My arm, I was really sore. I hadn't really thrown a baseball in a long time. And then, of course, there's some more dubious honors that I've experienced. This is me wearing a fish hat. And so it's this is some of my colleagues wanted to honor me in that way. We live in an exciting time. It's amazing when you think about the potential, but also the challenge. And so tonight I want to talk to you about how we can innovate our energy future. So what's the global reality? Well, the global reality is that almost 6 billion people live in energy poverty. About 1.3 billion people without any electricity at all. About 5.5 million people who die globally, who are dying around the world because of air pollution. That's outdoor and indoor air pollution. About 783 million people without access to clean water. And here's one I really wasn't aware of until we started researching it. About 1 billion metric tons of food is lost or wasted each year because they don't have the electricity to take it from the farm to the market. And so it gets spoiled. So that's the world we live in. Now, it's not all doom and gloom, because if you look back in the 1960s, the poverty rate has been cut in half since 1960. So there is progress being made, but we have a real opportunity to do something to make a change in the world. So the United Nations has their Millennium Development Goals, and so they list it in terms of education, health, they list in terms of environment, sustainability, child mortality reduction. And one of the conclusions from the United Nations was that without access to modern forms of energy, it's highly unlikely that any of these objectives could be met. So energy plays an important role in moving folks from poverty to a sustainable, healthy life. So this is kind of a busy chart, and I brought this huge laser. Yeah, that's what I'm talking about. I got this great laser here so I can illustrate this. So if you look at the chart here, I was going to step out a little ways. This vertical axis is called the Human Development Index. And so that index captures a couple of different factors, and so the health, education, and income. And so they talk about the quality of life basically on this vertical axis. Then on the horizontal axis, this is the total primary energy demand in gigajoules per year per person. This is how much energy is being consumed basically in these different locations, different countries, per year per person. Okay, this was the demand curve. So what it says, and what they found was that there's this correlation between human development and the amount of energy that you use. And it does make sense when you think about it. And so right now the US is at 330 gigajoules per year per capita, per person. And the HDI is 0.94. Okay, so that gives you kind of a sense. And so you can see on this little smaller chart here, here's the USA over here, and you can see these other countries all along this curve. And this 0.8 is kind of a transition where you'd like people to be above that number. So I started thinking, well, I wonder what the US was like 150 years ago. I thought, well, I wonder if this correlation is correct, and if it's truly time independent, which there's a lot of work that needs to be done to look at that. Then I looked up the energy consumption rate back in the 1860s, and in the U.S. we were about 90 gigajoules per year per person. So using this curve, that would put us around 0.75, and it was 80% of that energy usage was burning wood. So in the 1860s, the primary source of energy was burning wood. 20% was coal, and there were really small fractions of petroleum just starting to be used and some natural gas. But the majority really was burning wood. And so we went basically from this point all the way over here, and to me that was really encouraging. It took a long time. As the other forms of energy were being introduced, electricity in particular, the use of the large use of coal, it did help move our country from one end of the curve to the other to give us a standard of living that we can enjoy today. It also tells me that if you look at this part of the curve, it's fairly steep. And so what that means to me is that, that small changes in energy per capita could really move this line up very quickly or quicker. So developing nations, so if you look at where we were back in the 1860s, that's equivalent to where Brazil and Mexico are today. If you go back, if you look down here, this is India, China. So things are changing. But small changes in energy could really have a big impact. And there's lots of reasons for that. It's kind of a multiplicative effect. You have energy availability, now all of a sudden you got clean water, you have light, you have energy for your homes, you have more jobs, and it really accelerates very quickly on that end of the curve. So this curve to me was very encouraging, but there's also the big challenge. How do we bring almost 6 billion people out of energy poverty in a carbon-constrained world? So sure, when you can use all the coal and wood that you want and emit as much CO2 as you want, you can move along that curve. But how do you do it if there's a carbon constraint? So that's kind of what I'll be focusing on now. So innovation. So OSU is really world-class in terms of its energy research. And it's really kind of an all-of-the-above strategy where we're looking at all different types of energy, wind, wave, and of course nuclear energy, solar cells with photovoltaics, biofuel production, some low combustion, temperature combustion studies, nanofluids, you name it, the university is researching it. And it's a really powerful, when you think about the synergies that exist, and I think there's an opportunity for even more synergy between the different colleges and certainly with some of these major facilities. So we are working collaboration with the Hinsdale Wave Research Laboratory, ATOMI, which is right next door to us, and the Northwest National Marine Renewable Energy Center. So some of the work in wave energy is really important because when you think about the world today, by 2025, I think the 20 largest cities in the world will not be in the U.S. They will be, at least most of them, but maybe one or two. But they'll be in other countries, and about 80% of those are coastal. So having this kind of research going on right here in Corvallis and in Reedsport is certainly key to some of these communities that are looking for power. So I'll talk a little bit about the energy research that I've been involved in and kind of give you a little bit of insight into how do you create a billion-dollar company. Okay. So I'll give you all my secrets here. So you start with $4,000. So here we are, back in 1987. Now back in 1987, when I came, they didn't really have the big, what's the startup packages? They didn't have big startup packages. Well, in fact, I had no startup package. So I came, and I had a pretty heavy class load. Huh, what a great combo. So back in 87, when I came to Oregon State University, I did get a grant for $4,000 to study natural circulation. I was really interested in the idea of how you can cool a nuclear power plant just using natural circulation, convection. And that was before, it was just starting, this whole area of passive safety was just starting to be looked at. So I took my $4,000 and I went to Teledyne Wachang, which is, I think it's ATI now, and said, you know, I've got $4,000, I want to study natural circulation in a loop, and do you have any glassware? They said, sure, go get some students, bring a truck, we'll give you all the glassware that you want. So we went to Teledyne Wachang, picked up the glassware, came back, we said, okay, now we're going to set up this experiment. So I took my $4,000 and the glassware went to Portland General Electric. So PGE said, hey, what are you working on? I said, well, I want to develop a natural circulation loop to model the Trojan nuclear power plant. They said, great. We'll give you $50,000 a year for 3 years. I said, fantastic, that's wonderful. So as part of that work, I had to do a scaling analysis to show how do you model a large reactor using small-scale facility. So wrote a paper on that and presented that at a conference in Washington, D.C., and some of the folks from Westinghouse were in the audience, and they said, you know, Jose, this is really interesting. Do you think you can do that for our AP600? Sure, why not? So all said and done, by the time we were done with the AP600 work, we had built the Apex test facility with a 1/4 scale version of the AP600. We had spent about $5.5 million developing that facility, performing high-quality tests, and OSU came through. It's not easy to do because it has to be done by the university. So when I said, hey, we're going to do some nuclear safety tests right here in Corvallis, there was some skepticism, to say the least. Now, I had to explain that there was no nuclear fuel or anything like that involved. It was really just thermal hydraulics. There was no nuclear portion to it. And once we explained that, I think things went a lot smoother. So we spent $5.5 million, but the university had to change because the government has certain rules on your instrumentation that you buy and how you calibrate. And so the purchasing group on campus actually set up, dedicated one person specifically to do all those purchases for us and to keep certain records that would meet the government standards. So that was kind of interesting because the university had to adapt, and every time they adapted to something, I would give them something else. So it's been great. The AP600 led to the AP1000. So after we had completed that work and got the AP600 design certified, so in the US you have to get the Nuclear Regulatory Commission to certify the design before it could be built. As soon as we were done with that, Westinghouse came back and said, you know, we want to go to a larger size. We want to go to the AP1000 design. We said, sure. And we reconfigured our facility and ran another 4 years of tests. And all in all, by the time all was said and done, that group, we expended about $20 million on that project, on all those projects. What was great about it was that it was a collaboration between government, the Department of Energy, Westinghouse Industry, and OSU University. And it was a tremendous, this three-party collaboration was a win-win-win situation for everyone. I think we had well over 20 students who got either masters or PhDs on these test facilities just while we were working on it. And I know since then there's been more. So that was a great win for the university because all that equipment was funded by industry and by government, but we got to use it. In 2000, I had pretty much finished the work on AP600 and AP1000 with the help of my colleagues in the department. Got a grant from the Department of Energy. And it was called the Nuclear Energy Research Initiative. And they funded a project which we called the Multi-Application Small Light Water Reactor, MASLAR. Yeah, it doesn't roll off the tongue real easy, MASLAR. But the idea was that we would come up with a concept for a very small reactor that could be built in the factory, could be shipped to a location, and then it could be operated for 8 to 10 years, and then at the end of that time, you'd actually replace it with another one. So it's kind of like a battery concept. And because of my background with the Nuclear Regulatory Commission, my perspective was always from safety. I had a safety mindset ingrained in me from the 10 years I worked for the Nuclear Regulatory Commission. So for us, it was safety before the economics. We didn't even look at the economics of this thing. We just said, let's run a test and see how safe it is. And so in 2003, we ran the first test in the world to demonstrate the feasibility of using a small reactor inside of a small containment immersed in water. And it was a spectacular success. So in 2003, that data was available, and it demonstrated a new level of safety that hadn't been seen before. So when that was done, of course, what's typically done is that you finish your work on a project, you publish a paper, and then you go to the next project. So I was fortunate in 2004 to spend a year in Vienna with the IAEA, the International Atomic Energy Agency. So they work closely with the United Nations. And what I learned while I was there in talking to the delegates from the different member states was that there was a tremendous interest in small reactors. In particular, their concern was that, well, we need power, but we can't really afford the large 1,000-megawatt plants. They're very expensive. And also, we don't have the grid to support 1,000 megawatts. So they were looking for smaller scale power. So I had about 13 countries that we had put together a coordinated research program to look at these small reactors, and in particular this passive safety concept. So when we came back in 2005 from Vienna, we said, well, wow, there's a big market for this. And we got this thing sitting in the lab. It's a 1/3 scale version of this small reactor concept. We should move it from the lab to the market. How hard could that be? Sounds like a piece of cake. Yeah, so that was pretty hard. So from 2005 to 2007, we worked with the College of Engineering, and Dean Adams was the dean, and he was very encouraging at the time. And he lined me up with a business mentor who is Paul Lorenzini. I think Paul is here somewhere. So Paul had just retired from Pacific Power and Light as the president of Pacific Power and Light. He was the first nuclear engineering graduate from Oregon State University with a PhD. And he also was an attorney. I said, this is great. What a perfect match. So from 2005 to 2007, we made a lot of changes to the design to make it commercially viable, and to develop the intellectual property to make it investment ready. So by the time we were done with that process in 2007, we had the basis for 3 really strong patents that would become the IP for a new company. So in 2007, in July, Paul and I founded NuScale Power. Very exciting. So you can imagine two people going into a power company saying, "We want to sell you a reactor." It's pretty exciting. So we opened the doors. We actually had our first investors in January of 2008. We signed a technology transfer agreement with the university. By February of 2008, we had opened the doors, and we had a building, a bank building downtown across from the Burger King. It's a good landmark. And that was kind of the start. And we had that first investor who put funding in it was CMEA. Maurice Gunderson, who was one of our former OSU, who was a graduate of OSU, was the lead on that. And we grew very quickly to about 35 in that little building. And we continued to grow. And we went through the ups and downs. I won't say they were the usual ups and downs, but we went through ups and downs. But then Fluor became our partner in 2011. Now, Fluor is a global engineering, procurement, construction company. And in 2011, I think the revenues were about $20 billion per year, $40 billion in backlog, 60,000 employees. They were all over the world. And we were so pleased that they joined us as a strategic partner. So a strategic partner has a very long-term view, because they recognize that they can make a lot of profit in the long run if they get to build the plants. So they share that same long-term view. So strategic partner is different than the venture capital in that regard. So Fluor, a fantastic company to work with as our lead investor. 2013, NuScale won a $226 million matching grant from the Department of Energy. It was a matching, essentially cooperative agreement. So that was huge for us because that was a very stiff competition. A lot of companies, we were trading punches with the heavyweights. Let me just put it that way. There were some big companies we were competing against, and we came out on top as the sole selection in 2013. So that was huge for us. And of course, that was a matching program. So essentially, for every dollar that the Department of Energy put in, then our investors would put in $1. So that really was about a $450 million award. It was huge, and that's really what allowed us to move forward in a big way. We jumped from our 35 to 99 to close to 400 or more in a very short period. A lot of innovation happening. About 40% of our company now is under the age of 40. So about half, almost half the company is under the age of 40. A lot of innovation. I mentioned that we started the company with 3 base patents. And now we've got over 350 patents, either granted or pending in 20 countries. And that's because we've created this culture of innovation. We really encourage innovation within the company. We've had about 800 people work on the project. We have now 6 offices in the US, and we opened an office in London. So total, we have right now in terms of full-time employees, about 320 or 30 or so, and about 80 contractors. And next year, we expect a big spike back up again. So when you talk to NuScale folks, how many people have heard of NuScale? Okay, then. This is very good. So you probably live next to someone or know someone or met someone from NuScale. You know, we've brought in about 400 families and individuals to live within Corvallis, and so they're part of the community. And when you ask them about kind of what they view as the mission for NuScale, this is what we hope they say. But this is something that really resonates with all of our employees. We have a commitment to people, planet, and prosperity. So our mission is to provide scalable, advanced nuclear technology for the production of electricity, heat, and clean water to improve the quality of life for people around the world. And so we have a vision for something that's really much bigger than just producing power. It really is to make a change in the world, and I'll talk about how we're doing that. Okay, so how to build $1 billion company. So this is, it may be a little bit hard to see on this chart here. Well, maybe you can. So this is the mountain we must climb. So here we are back in 2000. We finished this work for the Department of Energy in 2003. We built a 1/3 scale test facility, which we operate here on campus. And that is an integrated test facility which models the reactor, the containment, and the pool. We formed NuScale in 2007. We started talking to the NRC in 2008. We said, we're coming in with an application. We wanted to go into what's called pre-application. We were acquired by Fluor in 2011. Now, an interesting thing about this is that how many people have heard of Fukushima? Yeah, a lot of people heard. So when that happened, I said, well, that's the end of the company. Now, what actually happened then was really remarkable because the phone started ringing off the hook. Because we had visited the congressional offices well in advance, and we said, you know, we got this new design, this is what we're doing. In terms of our safety, this is a new level of safety. This doesn't require any AC or DC power to be safe. And so that resonated in people's ears. And so when this occurred, the phone rang off the hook. They said, tell us about your design. And if your design had been at Fukushima, would this occur? And we said, no, we don't require any AC or DC power. Our seismic categories are much higher in terms of robustness. So that was, folks started talking to us. So Fluor invested in NuScale after Fukushima. So that's very telling, I think. So they were willing to step up next to us because they saw we had something that was very different in terms of what we offered the nuclear world, basically. We had our utility advisory board, so we have 29 utilities that we work with now every 6 months. And utilities have, I would say there's 2 things about utilities on our board. One, they are very risk averse. So they want to be sure that, that you've tested everything and that you know how your design is going to work. And they have no problems giving you their opinion. so they're not a shy group, that's for sure. So over the years, working with our utility advisory board, they've told us what they want to see in the design. So we've been working with the customer for many, many years, and we've tailored our design to meet their requirements, and you'll see that reflected in our design. We built a simulator, a control room simulator in 2012, and a lot of folks got to see that today from the college, so that was great. But that's a very impressive facility because we're controlling 12 reactors from one control room, and it is highly automated, and we're able to demonstrate to the regulator how you would do that. And the regulator themselves are also very impressed with this, and they've done many, many audits of that facility. First customer, UAMPS, the Utah Associated Municipal Power Systems, we got our first customer in 2013. So they've been working with us in parallel. They submitted all this paperwork to the NRC. topical reports, anything that was an issue that we thought might be an issue, we wrote a separate report and submitted that in advance to the NRC, to the regulator, so that they can be reviewing that well in advance. We got this is the DOE grant that we got, the $226 million. We've selected the site for the first plant, so that's been selected. We submitted our design certification application in 2016. So NuScale became the first small modular reactor application ever to be submitted for design review to the Nuclear Regulatory Commission. So we made history that day because no one had ever done that before, and up to this point, no one has done it since. So we've built a certain amount of steam and momentum behind our company that way. So our application now is under NRC review. And in fact, we've completed phase 1 of the review in 1 year, so, which is amazing. We're on schedule. And phase 1, there's 6 phases. And so you think, well, phase 1, that's got a long way to go. Yeah, it seems like a long way. But phase 1, the amount of work and effort that goes into that initial review was about 115,000 hours of review. It was the most intensive part of the whole review process. All 5 phases combined that are up and before us actually take less work than that very first phase. So we're really well into the design certification process at this point. We just awarded our first, and so right now this is the line we're at here. We've expended about $750 million to get to this point. Right now our spend rate is about $2.5 to $3 million per week. Yeah, the engineers are working hard on this. Okay, they're working hard, but that's a great boost to the community too, because these folks are highly paid. They live in the community and they're supporting the schools, and their taxes are helping, everybody. So we're excited about that. But it just gives you a sense of how big this mountain is, right? We just issued our first contract for the manufacturer. This was the first phase, the design phase for the manufacturer. So that's a real good indicator that we're moving very quickly into the manufacturing mode. So we awarded that to a company on the East Coast, BWXT. So they're well known for developing reactors, vessels for many, many years for the government. So very skilled. We think they're great partners to work with, so we're excited about that. So that just happened here just this past couple of weeks. Up here, the COLA, this is a construction operating license application. So the customer, so we're working on the design that gets certified, and then the customer comes alongside and they get the site certified. So the hydrology, water usage, all the environmental requirements, they have to work on that on their part. And so they'll get to a certain point and then they'll reference our design in order to build. And so at that point, once we have our certification here in 2020, we can actually start building that plant. So we're estimating that somewhere about $1.4 billion to get us to the point where we're able to construct. And that's not the cost of the plant. That's the cost to get us to the plant. I hear people, oh, wow. yeah. So when we were first talking to investors, and Paul and I were going around looking for investors, folks were saying, we don't know if you're going to be able to find investors for this because it's a pretty big lift, and we didn't realize this number would be as big as it is. We do know that now. But when we first started off, we were very enthusiastic, very optimistic, but still it was a big number. But this is amazing. We've made it a long way up this mountain, and we see a clear path in terms of funding and in terms of technology and in terms of licensing to meet construction of that first plant. Okay, so now you will all become nuclear engineers. So I'm going to talk a little bit about the technology, because I keep talking about these small modular reactors. It would be nice to know a little bit about what do I mean by that. So what we're doing is we're commercializing SMR, small modular reactors. And it's really an integral package which contains the reactor vessel, the containment, all submerged in a pool below ground. And that's kind of the whole technology. Each module will produce about 60 megawatts electric. And our first plant, for the first customer, they're looking at anywhere between 10 and 12 modules, up to 720 megawatts electric. What they like about our technology is that it can add modules as modules are needed, so you don't have to fill out the entire plant up front, so it saves them in terms of cost. And that flexibility that it can actually fit on a retired coal-fired plant site in terms of the footprint. So this is kind of a, let me see if I can do this here. Chief Technology Officer. Yes. So this is our reactor module. This is our core. That would be our nuclear fuel. It's about 6 feet tall, 7 feet tall, and so that fission reaction would occur to produce heat, and the hot water would rise because it's a lower density. So you have, and this over here are the steam generator tubes. It's like a helical coil steam generator. It's like 2 DNA intertwined. And so you have cold water flowing inside the tubes, hot water flowing on the outside of the tubes, and that heat rejection then produces higher density fluid on top of lower density. You have an elevation difference, a density difference, and it just gives you a natural circulation flow. So this design doesn't require any pumps inside the reactor. So that was an innovation in and of itself. On the secondary side, you have feed water, steam coming out, goes to a skid-mounted turbine generator set. So that's conventional fossil fuel 60 megawatt turbine generator set. You can buy as a package. You can deliver it, you can replace them very easily, and they're relatively low cost. This is the condenser box. So steam comes in, it goes through the turbine. That, as it comes out of the spent steam, then gets condensed in the box. And then now here you do have pumps, which goes to the inside of the tubes. So it's a very simple system, and each module has its own power unit. Each module has its own turbine generator set, has its own generator, and of course you can add these things as units. So you can start off with 1 or 2 units, producing 120 megawatts, and then later on you can pick up the phone and you can call me. Day or night, you can call me, and I'll get you another module right away. But they can order these modules as modules are needed. So it really is a different model for the deployment of nuclear. It's an installation as opposed to construction. So this is a little bit of the overview. So this is the module. That's all factory built. And that's the whole idea, especially we wanted to have this containment factory built. So instead of the big concrete dome that you're accustomed to seeing in nuclear power plants, what we've gone is to a small steel containment shell that you make in a factory. And there's some real safety advantages to doing that. Oops. So this module then sits inside of a reactor building. This is the reactor building. This is the ground level here, and this is a pool. So each module sits in its own bay in a pool. So this shows 5 modules on one side. There'll be 6 modules when it's filled out. And then there'll be 6 modules on the other side for a 12-module plant. So this is for the first customer. We're looking at single modules, 2 modules, 4 packs, a whole range of different combinations. Then this reactor building, which is a seismic category 1 building, sits over here. That's in the middle. These 2 wings here, that's where we house the turbine generator sets. So there'll be 6 on either side. The footprint is about 34 acres inside the fence, so it's relatively compact. This system could either use water cooling for the condensers or air cooling, and I'll talk more about that in a minute. It really does represent a new approach to the construction and operation of nuclear power plants. The idea that you can make these in a factory, then you can ship them by truck, rail, or barge to the site and install them. It reduces the construction time enormously. So you can imagine that you're doing all your civil construction on site, and while that's going on in parallel, you're doing all your fabrication of the modules off-site in a very controlled environment. And then it cuts the construction down from 5 to 6 years down to 3 years. So it's a significant savings in cost just because of this different approach to manufacturing. Safety. So one of the things we knew about early on was that this design would be very, very safe. And the big reason for it is that we're not using any active systems to provide safety of the plant. So we're using conduction through steel, we're using convection, natural convection of the fluid, we're using gravity to drive the flows. And so these were natural processes that did not require AC power or DC power really for safety. Because the modules sit below ground, we're seeing enormous advances in seismic capability. This is underground and in a pool. So one of the innovations from our company was that some of the codes that were being used in the industry, there's one called SASE. I think Dean Ashford is familiar with that. I'm not sure when it was developed, maybe in the 60s, 70s, early on. Well, our folks got a hold and created state-of-the-art codes, and which model not only the soil interaction with the building, but also the motion of the water and interactions with the modules. And we find that we have a significant advantage in robustness in terms of our seismic capability. So it's a big advancement, but part of it was because of the innovations that happened within the company. This is kind of an example of the level of safety that we can achieve with this design. So for this design, because it's a small core, about 200 megawatts thermal is the core, what happens is if you lose all your AC and DC power, you have a big earthquake and you lose the grid, so now you have no connection, no AC connection to the grid. And let's say they can't restore the grid, so eventually your DC power disappears, right? In this design, we don't require any AC or DC power. In fact, this reactor will shut itself down without any AC or DC power, without any operator action, without any computer action, and cool itself for an indefinite period of time without adding water. So it transitions from a water-cooled system to an air-cooled system without any operator action. So the way it works is that you have this big containment shell sitting in the pool. We have safety valves on this system, and because there's so few of them, basically 5 on the reactor vessel, that during normal operation they're held shut with power. You lose power, they spring open, and that's it. That's all you have to do, is let those valves spring open, just a mechanical spring. And at that point, you're venting steam into the shell, and that steam inside the shell is condensing. The heat's being conducted through the steel wall and being deposited right into the fluid directly. And it'll do that continuously forever without ever uncovering the core. So in 1 second, the control rods drop because they're held up by electromagnets. They fall, they shut down the reaction, but you have to remove the decay heat. And so in a day, you go from about 10 megawatts or so to about 1 megawatt. In 3 days, you're down to about 800 kilowatts. If you didn't add water or you didn't cool the pool, after 30 days, you'd be down to 400 kilowatts. And you have so much surface area that just the motion of air against the shell is sufficient to remove all the decay heat. So we move from a water-cooled system to a boiling system, the air-cooled system, without any operator action. That has some really interesting consequences. So recently, the NRC actually approved our design, and we're the only design that's ever been approved for this feature. If we apply our safety method for our design, the NRC agrees that we do not need what's called 1E safety power. Okay, they're basically acknowledging that this design doesn't really require power. They issued a safety evaluation report on our methodology and indicated that indeed we don't need this classification 1E safety power. That's huge. That's really huge. You all should be like clapping like crazy. Well, thank you. Yeah, so that took a lot of work, and again, it's never been done before. But now what we're seeing is in our emergency planning. So we've also submitted our methodology on how we size our emergency planning zone for this design. What we found is that for the worst case conditions, And by worst case, I mean these are events that would happen once every 3 billion years, okay? We said, the likelihood of core damage for our fuel is once every 3 billion years. That's the frequency. Think of, like the age of the planet. So it's very unlikely. But we went one step further and said, well, let's assume it happens. And let's analyze that. And so we analyzed that situation. What we found is that at the site boundary, I mentioned that 34 acres, or depending on the site, maybe 70 acres. At the site boundary, we're not able to see doses that exceed the regulatory limits at the site boundary. So the question of, well, how big is your emergency planning zone? Well, we're saying it's inside the site. Again, it's never been done before, but we're quickly moving down that path because the regulator recognizes the analysis. There's 3 things that will happen to validate that. The ultimate being an emergency preparedness rule, which would get issued in 2020. But we're well on our way to that. We are working with, we provide our calculations to the Tennessee Valley Authority, TVA, and the NRC issued a letter indicating as part of their audit that if a NuScale plant was sited at the Clinch River site, owned and operated by TVA, that they would be approved for a site boundary. It's never been done before. You all should be like clapping. I'm just trying to keep you awake. So if you've ever worked with a regulatory agency, they don't take you just by your word. You have to demonstrate everything. You have to test everything. So we're getting close to about, we're somewhere between $80 and $100 million in testing that have been done to validate our different components. So our fuel bundles have been tested. They've been built, tested, seismically shaken, and a whole range of testing that had to be done. We did what's called critical heat flux tests. Those tests look at what's the maximum heat that can come out of your cladding in a safe manner. So we know the limits of our fuel. We just completed our control rod assembly drop test. And what we did was we just picked the best testing agencies around the world who we were working with on specific things. So like the helical coil steam generator, that's a big test. That was a full-scale test that we ran in Piacenza, Italy. So my wife and I got to visit. They're located just south of Milan. What? We went to the test facility. So that was a full-scale test, and we've got additional tests being performed now. Flow-induced vibration test. We've done inlet flow orifice tests for our steam generators. So we're building the hardware at full scale and testing these things. Tube inspection testing that has been completed, looking at how do you look for cracks inside tubes. So we actually came up with a patent based on that work. Fuel tests I mentioned before. So those are actual fuel bundles that are being tested. These are electrically heated, but they take them to very, very high heat fluxes, well beyond what you expect to see in the plant. Control rod test. If you go up Highway 99, going up north, you'll see this facility, and you wonder what that is. That's the upper 1/3 of our module. So we actually built it full scale, but it's just the upper 1/3 piece. So this is the containment with the working platform on top. And inside here is the top of the reactor vessel with the control rod drives and things like that. So this is actually a full-scale version of the containment and the reactor head. And we did that so that we can plan our in-service inspection and maintenance work. So it's great because the engineers will crawl all inside there, and they'll see if they can actually do the procedures. And where they find a problem, they'll identify that, and we'll change the routing of piping and stuff inside the design. So it's a really good tool in terms of assessing our maintenance program. And of course, our real workhorse facility has been the NuScale Integral System Test Facility right here at Oregon State. It's located at the Radiation Center. Somebody wanted to clap. That's been a great facility. That's an integral test, and the reason that's been so important is because we're looking at all the phenomena on an integral basis. We're looking at how the reactor interacts with the containment, how the containment interacts with the pool, and we have to model that with our computer codes. So what that does for us then is it provides a reality check for our safety analysis computer codes. It also provides an enormous amount of data which is provided to the regulator so they can assess their own codes, they can assess the data and their codes independently. So that's been a great facility for us, and we continue to operate it. We just are now doing another, I guess it's going to be NIST 2, another upgrade to that facility to reflect the current design. This was a big one. The integrated system validation, and that's now completed. We had to demonstrate that we can control 12 reactors from a single control room, and we had to do it safely, and this was a real important test for that. So this is a performance-based evaluation of our hardware, our software, and the personnel. So we actually hired about 22 reactor operators. So there was one group that had a lot of experience in the current fleet, working with reactors, operating reactors. Another group which didn't have a whole lot of experience. And then a third group which were just basically students who had just graduated from university. We mixed and matched those and created 3 crews of 6 licensed operators, and we put them through the training. So they were trained just like they would for the real plant. They received 56 classroom lectures over 9 weeks. There were 36 simulator sessions for each crew over 10 weeks. And at the end of that, they had to perform 12 what are called full scope scenarios. And so this is where we get to throw everything but the kitchen sink, maybe sometimes kitchen sink, at them, and we would see how they respond. And so at this, we're doing human factors engineering studies and human system interface studies as this is all being done. We're collecting all that data, and then for 2 weeks of that evaluation, the NRC inspectors are in the room, and they're watching these operators go through these different scenarios. And there'll be crew reductions. We'll get down to 3 operators with multiple issues, and they have to be able to handle that. They did amazingly well. This system and this design is really intuitive. So they learned it, and they were able to execute this really flawlessly. The NRC was very impressed by our conduct of operations. It's really impressive to see when these folks are in the room, these young men and ladies, just eating this stuff up. It is geared for another generation. So I go through and I click and I look for stuff. But you bring a younger generation in, and it's very intuitive. They can find everything and they can click through the stuff. The unique feature of our design is that there are no operator actions required to assure the safety of the plant. No operator actions required for the safety of the plant. So, and these are called design basis accidents. So the only time you would actually take actions would be for beyond design basis, is like the 1 in 3 billion year event. That gives you a whole level of confidence and ability to really control the plant and rely on the automation. It's an all digital control system. So it's very different than what's being used in the nuclear industry today. So now this part here, let me step over here. This now starts feeding into this idea of the global mission. Okay, the NuScale Diverse Energy Platform. So we started looking at this. We said, this is not just a power plant. This is an energy platform. What we want to do is provide not just electricity, but we want to provide clean water and other things. So we actually collaborated with national laboratories. We collaborated with universities on different studies. And so we did like 5 different major studies, and we published the results. So we worked with Fluor. We said, Fluor, tell us about oil refineries. So we teamed up with Fluor and said, let's assume we have a 10-module NuScale plant connected to a 250,000 barrel per day oil refinery. Could we reduce the carbon emissions? So it turns out we could reduce, just by providing electricity and process heat, we could reduce CO2 emissions from a 250,000 barrel per day oil refinery by 40%. That's pretty cool. So the reduction was about 190 metric tons of CO2 per hour that we can reduce. We then did a study with Idaho National Lab on hydrogen production. So Idaho National Lab has a process they call high temperature steam electrolysis. So they wanted to try their new process coupled to our modules. So a 6-module plant could produce about 200 metric tons of hydrogen per day, of very high purity hydrogen. So that's important. If you look at the numbers, I think in terms of energy and some of the work that's being done here at OSU with fuel cells and the opportunity to have fuel cell driven hydrogen cars, this would be a huge, huge benefit for that. The other study we did was on desalination, and so water, again, was really big. One module, one 60 megawatt module, we looked at reverse osmosis, we looked at a whole range of technologies, and we published these studies. And what we found is the 160 megawatt electric module could produce 60 million gallons of clean water per day. Yeah, 60 million, yeah, that's huge. So a 12 module plant could provide all the water needs for a city like Cape Town, South Africa. All the water needs, one plant. So it's pretty impressive. I'll talk more about wind and renewables in just a moment because it holds a special place in my heart. Okay. And I'll talk about mission critical facilities also. So we've looked at different applications and we find that there's really opportunities to do this. So this is the clean water. So we wrote a paper which got published at a conference in France. And it was really interesting. We raised the question, can nuclear and renewable be friends? We really want to be friends. Okay. For some reason, we have some, not everyone, but and certainly not in the university. I think at OSU, folks work very well collaboratively. But in other places, nuclear and renewables don't seem to get along. So I said, we need to be friends. So our design, we developed what we call load following. So one of the challenges with the penetration of renewables like wind and solar is that they fluctuate. You know, the sun doesn't shine all day and the wind doesn't blow all the time. So you have fluctuations. And if you get to a certain penetration level with renewables, you lose grid stability. So that's a problem. So when we talk to our utilities every 6 months, they say, wow, what do we need a design that's flexible enough to do some load following. So we came up with a load following. Now these 3 shaded bubbles look kind of neat. There's a huge amount of reactor physics that goes behind looking at developing the boundaries for these bubbles, okay? So we actually have 3 modes of load following. We have our design, because it's small, you can take 100% of your steam or any fraction in between and dump it directly to the condenser. So we bypass the turbine. That's called a turbine bypass. So if you have immediate fluctuations and you have to change power very quickly, we can do it with the turn of a valve, and you just redirect some of the steam to the condenser versus the turbine. Maybe not the most economic way to do it, but for very rapid changes, we can do that. The second is module down power. So what that means, and this is more for the kind of the 1 day range, a couple days. This is in the hour type range. Our central control rods and our design is flexible enough to where we can raise and lower power just with those control rods. And we have a really good maneuverability, which was surprising because it's a natural circulation system. We thought we wouldn't have this level of maneuverability, but it works really well. So that's kind of an intermediate. Over time, we can raise and lower the power of 1 or more reactors and do that load following. The third is module shutdown. So basically, we can say we have 12 modules. You're going to use water from the dam for the next 2 months. We can actually shut down a module for 1 or 2 months, depending on what the customer wants to do. So we've added a lot of flexibility to our design, which we previously haven't done with nuclear, and our core is designed to do this in order to be a good partner with renewables. So we would like to be friends with renewables. This is a study, and so our first customer, UAMPS, like most of the utilities we work with, they all have wind power or solar power. We did do a study. Right now they have about 57, almost 60 megawatts, and it occupies, this is wind power, and it occupies about 17,000 acres. So it's a really big wind farm. So they put a lot of space between these. And this just shows a typical demand curve. This shows the wind farm output. And this shows what we would have to do in order to keep that up. One of the studies I'd like to pursue now is that we can use some of the power shaping to reduce the amount of steam that we dump to the condenser, to reduce the energy losses there. So I'm looking for some really clever AI people, artificial intelligence people, to work with us because we think there's some opportunity to do that, because weather is really hard to predict, but with AI, they're doing some amazing things. The other thing we looked at is the solar power, and this is the duck curve, so-called duck curve. It has nothing to do with the ducks, right? So it's just called the duck curve. But this is what's being predicted for 2020 for California. So this is the ISO curve. And what it shows is that at the end of the day, of course, the sun's going down, so you're losing power. But people are going home, they're turning on their TVs, they still have TV, yeah, their plasma TVs, their fancy computer things. They're using a lot of power in the evenings, right? They're cooking and all that stuff. So the power demand goes way up. Well, we designed our system so that we can ramp up. We can go from 20% power to full power within 96 minutes and actually address the duck curve. This is getting a lot of attention right now in what's called the energy imbalance market, which I'm not real familiar with, but it sounds like this is a real opportunity for us or for our customers to be part of that EIM. Another aspect of our design, we finished about 3 years of additional studies. So the NuScale Diverse Energy Platform studies, looking at different applications, was about 3 years worth of work. This is another 3 years that we worked on plant resiliency. So again, these are different studies that we've done and published. My vision for NuScale's vision for nuclear is to become first responder power. Okay, first responder power. So right now in the nuclear industry, if all nuclear power plants are required to have two connections to the grid, two independent connections to the grid. And the reason they have those connections is to assure that you always have power to your safety systems. And they have a lot of reliability, so you have redundancy, then you have lots of redundancy in terms of backup diesels and things like that. Hurricane comes along, knocks out the grid, and so now you're relying just on diesels. Well, in our design, we don't rely on any AC or DC power, so we don't need the grid. And so I'm moving us to become an off-grid, to get approval to be off-grid operator. So we have island mode. It's a feature of our design. If you lose the grid, any one module of the 12 can pick up all the house loads for the entire plant. So now you're working like a little island. So that's providing the power. So now the lights can go off everywhere, but that plant is still up. One module is producing power for the plant. The remaining 11 modules are dumping their steam to the condensers. And then as soon as the grid is up and available, we can start dispatching power in 60 megawatt increments. So as soon as sections of the grid are restored, we could be the first ones to respond. So we really reversed the role of nuclear power in this regard by becoming first responder power. We built an enormous resilience. Most nuclear power plants have resiliency built into them. So I showed you the reactor building, which houses the pool. That building was designed for 290 mile per hour winds, sustained winds. And for tornadoes, and for the projectiles that tornadoes will lift at those velocities. So it's a very robust building. In terms of seismic, we could withstand Fukushima-type seismic events. And a big part of it is because most of the building's underground. We don't have the large lever arms up high. We can withstand hurricanes, tornadoes, floods, so it is very resilient. We had to design it, this is a post 9/11 design. We had to design the building to be aircraft resistant. So aircraft impacts, we designed for that. Cybersecurity is another big one. We went to a very different design for our module protection system and plant protection system. We use what's called field programmable gate arrays. It's kind of like a hardwired package. So you can't change that programming. So even if you were connected to the internet and you had a cyber attack, that program can't be changed externally. So we made a big step forward in terms of cybersecurity. And then lastly, and most recently, we completed what we called our electromagnetic pulse studies. I was surprised. When the experts gave us the results, they were very impressed with our design, and they said, you know, it's a really nice document. I mean, they did a lot of work. And they said, you know, this is the state of the art. This type of study has not been done for the power industry in a long, long time. And what you've done is something much more advanced and much more detailed than's been done before. So they said, you know, the rest of the power industry would really love to get your results. So we did get a request from the Department of Defense and from the Department of Energy to share those proprietary results. And we're working now with some of our OSU colleagues, the Palmers, to put together a non-proprietary paper. And I think that's going to be submitted in November in Orlando. Orlando, huh? Yeah, so that should be nice. So that's a major study that's been completed, and again, it's groundbreaking stuff. How do you survive electromagnetic pulse? So I didn't even describe. You know, if you're not familiar with electromagnetic pulse, you have a coronal mass ejection from the sun, interacts with the atmosphere of the Earth and produces an electromagnetic field which interferes with wires and stuff like that and messes up your electronics. You can also have a high altitude pulse, which is due to kind of a weapon sort of a thing. But we analyzed all of that, and it really is a pretty impressive study. And our plant does really well. This is another area of interest. We're working with a joint study with TVA currently. We have two types of studies. We already published one. The second one is coming out, and then the TVA study will come out here probably by the end of the year. But, you know, we have a 12-module plant, and each module is a separate power unit. And so as a result, what we find is that, overtime, 6:30. Am I way past time? I've been talking for, you got to give me a signal, man. Okay, I'll get it wrapped up. Yeah. Okay, all right. I said, wow, this is going fast. I'm having fun. Okay, good. We have a 12-module plant, and each one of these units is a separate power unit. So if you think about what's done in the computer industry to have reliable storage memory, you have what's called a redundant array of independent disks, right? So what we have is a redundant array of independent reactors. So when you do the studies, we say, well, we can provide greater than 95% capacity to the grid at any time. But if you ask the question, well, if you have a mission-critical facility on a microgrid, and you're connected, and you have a NuScale plant connected to that microgrid, and you don't need 720 megawatts. You only need 60 to 120 megawatts. So it's a subset. You only need 2 out of the 12 or 1 out of the 12 modules to be available at any one time. What you find is that for a mission-critical facility like a hospital, data center, you name it, things that have to have power 24 hours a day, 7 days a week, we can offer them 99.95% availability for the 60-year life of the plant. So that's a huge, huge improvement in terms of availability for a microgrid. So that doesn't include the reliability of the microgrid. It assumes that the microgrid is going to survive these different events. At 60 megawatts, it's 99.99%. So our utilities, who we're working with, TVA, said, oh, that's nice, okay. But we want 6 nines. Saying, okay, 6 9. So, but there's a trick to that. So they're saying, what if we took a NuScale plant and replaced some of our coal-fired plants with a NuScale plant? So now you're adding to the grid a higher reliability plant, and you can take advantage of the fact that you can have multiple power units providing power to that mission-critical facility. So that report will be published here pretty soon, but I'll tell you what, we're just at the 6 nines. So it's pretty impressive, yeah. It's pretty impressive. We're excited. But that, again, this is something that when we talk about reliable power and longevity of fuel, we did a study also looking at what happens if you have a major catastrophe where you lose the transportation infrastructure. You can't get fuel to the site. Well, we found that we could provide power to 120 megawatts electric power to a mission-critical facility for 12 years. Because now we're taking fuel from other modules and just replenishing the ones that we need for power. So it's a very robust, very resilient facility, and again, it offers a whole other level of reliability. We are the first SMR to undergo licensing in the US. That was a huge effort. We spent about 2 million hours developing all the work to get to that point. 800 people, 50 suppliers. We spent about $500 million to get the design to the point where it was ready to submit. And we submitted 14 topical reports to support that. So those are additional licensing actions. We are on schedule. We are on track to get that final safety evaluation report September of 2020. So we're less than 2 years now. Remember? Yeah, that's good. So we started, you remember we were on the bottom of the mountain there, like in 2000. It's only taken 20 years. Yeah, kind of like that. Our first customer, UAMPS, the Utah Associated Municipal Power Systems. So they're a consortium of about 45 smaller utilities and municipal power. And 33 of the utilities, a subset, said we want to participate in the project. We now have 29 power sales contracts which have been signed with that group, and we have additional meetings with them coming up. So we look to have at least 150 megawatts committed by April, and the Department of Energy is also looking at the potential for using some of the modules at the Idaho National Lab. It is a global market. So what I observed way back in 2004 in Vienna was really true. You'll see different values, but they say that by 2035, this is about a $100 billion market. If you look at other studies from 2024 to 2042, it's somewhere around $400 to $500 billion market. So if we only get, and this is just for the SMRs, that's not for all power, that's just SMRs. And if NuScale just gets a 20% share of that, right? So when we talk about factories and what we're looking at in terms of factory, to keep up with the demand for just 20% of the market, SMR market share, we would have to be producing 3 to 6 modules per month. Okay, and over the year, that would be for a manufacturing firm, that would be about $3 to $6 billion manufacturing facility. Revenues. So that's huge, an incredible number of work opportunity. So when we talk about our manufacturer or our supply chain, we look at that as an economic engine for prosperity. Okay, the idea is that you're building factories, which is bringing jobs, and that's an opportunity to really increase the economy. And that's a huge factory. We have selected our manufacturer, BWXT. So they're a Virginia-based group. They're very capable. There are a lot of modules lining up to be shipped out. We went through an 18-month process. We received interest from 83 companies from 10 countries. People know about NuScale, and they want to be part of that economic engine. And for the first time ever, what I've shown you previously is kind of the working design in terms of, it's the engineer part of it, right? We say this is the reactor building, this is what we need to have in the reactor building. Now we bring in the architects and the artists, and they're saying, oh, this is what it could look like. And so this is a preliminary rendition, but this shows what a NuScale plant, a completed plant, would look like. It's kind of futuristic, isn't it? Yeah, it's pretty cool. It's like the Enterprise or something. Star Trek fans. So this is the reactor building. It's still, if you look underneath this shell, the reactor building's there. It's the same layout, but and some of these features actually are design features used to improve our electromagnetic pulse resilience, which is kind of interesting. So we're excited about the future. This is going to happen. So I'm going to finish off here with a quick video here.
The energy that powers us has changed over time. Innovation, ingenuity, and curiosity transform how we fuel our lives, allowing us to do more, to be more. Today, Reliable energy enables many to live the human experience to the fullest. But not all have access. We all deserve to experience what it means to truly be human. And yesterday's energy has done all it could. Once more, innovation, ingenuity, and curiosity conspire to break through. It's time we outgrow what we think are our limits, to open our eyes to a better path toward the energy we need. A better kind of energy for humankind. Smarter, cleaner, safer, and cost competitive. It starts by reimagining what's capable and creating energy that can take us further. It starts with us, for all of us. NuScale, power for all humankind.
Thanks so
Will you
much.
answer a few questions?
Oh, sure, yeah.
Okay, we have a few questions. Well, first, Jose, that was an incredible story about innovation. Let's give him another round of applause, please. Okay, so we have a few minutes for questions. We do want to get out of here by about 8, but we have a couple microphones in the front. If you have a question, please come down to either one of the microphones, and Jose will be happy to try to answer them.
I'll try my best.
You had a slide that showed, I think, 17,600 acres for a 60 megawatt wind farm, while talking about just 34 acres for 60 megawatt per module nuclear, small nuclear reactor, right? Why would we do wind?
Can renewables and nuclear be friends? Thanks for your question. Yeah. Okay.
I would like to agree with you about nuclear power. At the same time, the strongest and most persistent objection to nuclear has been about nuclear waste. And I know that you are not responsible for the magnitude of that, but can you reconcile your work and your projects with the nuclear waste situation today?
Yes, let me see if I can go back to a slide. It's a little hard to see. So the waste issue is one, it's the used fuel from a nuclear reactor. So in our design, we would use the fuel element in basis 3 batches of 2 years. So 2 years it would run, then after 2 years we would shuffle it and run it for another 2 years, and then we shuffle it one more time, and it would be like 6 years. At the end of 6 years, we would remove that fuel element, and that's called nuclear waste. It's basically unused or used nuclear fuel. At the end of that time period, about 95% of the energy content is still in that fuel. Oh, that got quiet. But 95% of the energy content is still in that fuel. So that's why many countries reprocess or recycle that. And so that's a potential use for that fuel. But I did want to show what we did with what we're doing with our fuel for our site. And I mentioned this is 34 acres. You see this little corner here? That little corner is where we would have our dry cask storage, which is the best practice today for nuclear waste. That little area houses all of the spent fuel from all 12 reactors for 60 years. It's all in that little space. So we're not, in our design, we've really worked very hard to keep the volume down of the fuel, but even beyond that, if that fuel is available for reprocessing, you could reduce that volume significantly further. So we're not talking about a large volume of waste for a 12-module plant. So at least that gives you kind of a perspective. Where we are now is the question, as a country, we need to make a decision. The technology exists to reprocess spent fuel. Other countries are doing it. it's something that we could do. Uranium, however, is very inexpensive, and so to reprocess, I think there's going to be some economic case that's made for that. Okay? Yes, next question.
The waste question was already asked and answered, so thank you. So my next question is, so you guys spent about $750 million and you're going up to spend $1.4 billion. You haven't told us, you told us how good all this is, but you haven't told us how to invest.
Oh. Well, let me get my... Thanks, what a wonderful question. What a wonderful question. Yeah, we're looking, I can't say a whole lot, but we're looking for that great day, you know, when it's open and available for people to invest. Any more questions? Oh, yeah.
Yes, good evening. And first, of course, thank you very much for taking your time and enlightening us all on the project and the amazing success you've already got under your belt. My question is regarding the state of nuclear power as it is and what other types of power we use within this country. Hydroelectric's been extremely popular, and in the 20th century we had a building boom of hydroelectric plants. Now, we're looking at bequeathing to our children the monumental tax burden of maintaining that infrastructure. Is this the heir apparent to the hydroelectric system that we've built our 20th century success on?
Great question. I mentioned we work with these 29 utilities, and they all have coal. Most of them operate coal-fired plants and have some mix of renewables. Most of their coal-fired plants are 40 to 50 years old. And so what they like about this design is that you can take a retired coal-fired plant site, use its transmission lines and its water, and build a NuScale plant right on that same site. And because we're looking at a site boundary emergency planning zone, it actually would work within the community. So when I think about heir apparent, I think more of the coal, some of the coal-fired plants that are closing down because they're too expensive to replace, to upgrade and replace. So I kind of think that the NuScale module fits really well as the heir apparent to some of the coal-fired plants, more than hydro.
Okay, I think we have time for 2 more questions. We'll go with you and then we'll go.
I actually had a couple of questions, but I'll let you decide which you want to answer if there's enough time. One, the other end of this is not the spent fuel, but the supply.
Right. And
given the international conditions of today, the uranium supplies may be questionable if you have a large build-out like you're saying. So that would be one question. Another question is, and this is really blue skying, and it's about fusion. Do you see your platform being in any way a bridge to a fusion power system? Is there any potential in that? So those are my 2 questions.
Yeah. Okay, quickly, uranium supply. We have a design for our core, which is thorium-based also. So we are looking at other potential. Some people know about thorium, okay. So we do have that would be one option. So we're looking at that right now. And we actually did a study back in 2003. We're renewing that study. The second, with fusion, I got into nuclear engineering because of fusion. So this is 1973, yeah, a long time ago. And at the time, really, I went at the University of Florida in Gainesville. They showed me their little tokamak type deal, and they were really confident that it was going to happen in the next 20 years. And it's a big lift. But if there's a lot of companies right now, I think if you look at the new startups now, there's about 70 companies now looking at nuclear power, all different kinds of design, including fusion. And you never know. There could be a breakthrough. But I think it's going to come from a very innovative, my sense is that it's not going to come from the big system, it's going to be from a small system. And it's going to be different than what people were thinking about. It's going to be very innovative. So I think there is hope for fusion. I don't know when, but I think it's still coming. Yeah.
Hi, Jose. How much do you estimate a 720 megawatt plant would cost in today's dollars?
Well, I got my order book, so we're looking at just under $3 billion. So for our first of a kind plant, and so the utilities have given a very specific target in order to purchase. They're saying that in terms of, and they're looking at the levelized cost of electricity. So saying the target is you need to be able to generate power about 6.5 cents per kilowatt hour. Okay, that's the target. And so we've worked very hard to get the price down low so that we can meet that levelized cost. But it's about $3 billion for a 720 megawatt.
All right, thank you.
Mm-hmm.
All right, thank you. And let's give Jose another round of applause.
Thank you very much. Oh. Wow. Wow. Come on, guys.